Welcome to our last section on graph theory. We're going to talk about trees. Section 10.4 is all about trees, which are a very important concept in statistics because mathematics use that concept a lot. So let's go through what are some basic ideas in terms of trees and so forth. So a graph is circuit free, or remember, cycle free. I don't know why your book doesn't ever use cycles. It's a more common term. If it only has no cycles, and a graph is a tree if it only is cycle free and it's connected. A trivial tree is just a single vertex, and a forest is pretty much a bunch of trees that are not connected to each other. So let me just draw for you a couple different trees to kind of illustrate this idea a little bit. One, this would be a tree. Now notice I have no edges. If I added this edge right here, it would immediately have a cycle, and therefore it would break the fact that it actually is not, that it is cycle free. So trees have no cycles. All right. Next. Oh, I also want to show you something to remind you about what are cycles and so forth. So let me clear this off for a second. This is being weird. I apologize. Okay, something's going weird. All right. So, sorry, I had technical error real quickly, but I'm going to draw a tree. This is a tree that I have drawn. And then over here, this is a cycle. So remember, the definition of trees and cycles has nothing to do with their actual shape. It just has to do with if they're connected or not. So on the left-hand side, we have a tree. This is a tree, and this is a cycle. By the way, this is a joke that my father absolutely loves. But it illustrates the idea about how what is necessary to have a tree versus what is necessary to have a cycle, that we're looking at connections and so forth. So let's look at some more different examples. Here are three different trees that we actually could look at. All of these graphs right here are trees. And that's because notice none of them have connect back and they all split out. Even this single dot is a tree. They may be organized in different ways, and there's different ways to often organize a tree. We can talk about different things. If we come to this one is not a tree because of these three vertices right here. Since they form a cycle, we have a problem. Again, if this is truly a simple graph, then we're not dealing with this particular situation, but this would still form a cycle, which is a problem. This, again, is a loop. It causes the problem. And these over here are not a tree because they're actually two trees. They're not connected, therefore they make a forest. So it's all about, do I have a forest or do I have a tree? And that's kind of idea. So let's talk about some examples of trees that actually you use. One of the common ones, and especially if you're doing computer programming, is we use a lot of decision trees. We actually draw a lot of our computer programs, and we kind of do decision trees or do flow charts to show how it flows through the program. And decision tree will kind of help illustrate this idea. Where notice I have here a bunch of vertices. And so they're going to take a score on part one. If it gets low enough, they automatically go to math 100. If it's below 8, they go to 100. If it's 8, 9, or 10, they have to take part two. If that part two is also below 6, they still go to math 100. So they might do well on part one, but not so great on part two. And if part two is bigger than 6, then they get to go to math 110. However, in the first place, if they had their initial part bigger than 10, then we go to part two and we say, okay, what's that? If it's small, they go to math 110. If it's big, they go to math 120. And this is exactly how we can kind of work our way to this. So let's read this tree. And as I said, we're just going from left to right, see if they had a score on 9 on part one and 7 on part two. So from here, a 9 is going to take me down which of these 3 branches? Takes me down this one right here to their score. And they had a 7, which is bigger than 6, so they go up here. So they're going to go to math 110. So because of that, we get here. Now, here is why another reason why trees are beautiful for all of you. I don't know if any of you didn't realize this, but natural language processing, the basis of a lot of LLMs, actually use trees because a lot of grammar can be used to be derived from trees. This was actually developed, ironically, initially by an English person, and then we've shown it mathematically. So if you have a English grammar, you have a sentence can be produced by first a noun and then a verb phrase. And a noun phrase can be written by writing an article and then a noun. And then, so let me show you an example of this. And then an article phrase can be produced by writing an article and then an adjective and then a noun. And a verb phrase, so there's 2 different noun phrases I can do. I can do article and then a noun, or I can do an article, adjective, noun, and a verb phrase, the verb, and then a noun phrase. So notice a noun phrase is a verb phrase. So let's consider the article is one, the adjective is young, one verb is caught, the other is one noun is man, and the other noun is ball. The rules of grammar kind of help us understand how we can actually put these things together. And we can kind of, I know you may of us be like, the young man caught, the young man caught the ball. But what we remember we have to do is we have to do a noun phrase. So we have to start with a noun phrase first, which is an article and the noun. So I could have done, I need an article. I only have one article. It's the ball. And that would take care of this thing right here. Next, a noun phrase can be produced by writing a noun and then an adjective. I could have done the young ball and then have to follow that with a verb phrase. Well, the verb phrase is a verb followed by a noun phrase. Well, that'd be caught. And then I have to do a noun phrase, which is an article, the man. So I could write the phrase based on this, that the young ball caught the man, but that doesn't always make sense. So let's kind of just see how this is going to end up working out. So in 1959, again in 1960, the computer language ALGOL was used, the brackets newer notation. This is where we use some different things that some of these are leaking into some of the notation you may have already seen, which is I'm going to have a bracket are used to enclose the terms, and then a vertical line to represent the word or. So notice, number one, I have a sentence means I have a noun phrase and a verb. That means I can have a noun phrase, an article, and a noun, or I can have an article, adjective, noun, because it has to go in that order. That's what those second 2 things, that's where the or came into play. Verb phrase equals verb, noun, phrase. Article is the, adjective, young, verb, caught, noun, man or ball. So this is literally what it's going to have here. It's going to go sentence. It's going to have noun phrase, verb phrase. So the article has an article, which is this. Adjective, there's only one. Noun. The young man caught the ball is one of the possible options, but it's not the only option. So that's why we have this thing that kind of derives from this. And it also kind of helps. Now, in the study of linguistics, semantics, it talks about grammatical structure of sentences. And semantics refers to the meaning of words and their interrelations. In other words, how are they connected? So if you switch 2 words or something else, as it says right here, a sentence can contain uh, like you could have said something like the young ball caught the man. And that is nonsensical because balls can't be young. So I'd have to have some kind of rule about the fact that a ball cannot be young and a ball can't catch something. See, when you put this just into a computer and it knows none of that information, it has to learn that information. And so this is again logic that has to be implied. And this is how AI partly works. If a sentence then can contain syntactical errors, it can also have semantic ones, which is why I can say like me hungry. Or uh I was just wanting to say a Yoda phrase and I just lost it. Yoda's known for things. Um Yes. Like that is something that would be a Yoda phrase that Yoda would say. If you don't know what Yoda is, well, good luck to you. Google it. Anyways, one of the key other things that I've not mentioned yet about trees is how do we characterize them? How do we talk about a tree? Well, one of the main things we talk about trees is how many vertices and how many edges. It turns out that those things are completely fixed for any tree. So if n is any positive vertex, you must have n minus one edges. And this actually goes back to the pigeonhole principle. Since it's connected, every vertex must have an edge connected to itself. Okay. And we can also do this doing an induction proof is another way to show this. So we can say, let's start with a tree, and we show that I have two vertices. I have two two vertices and one edge. Boom. Then I suppose it's true for some k value and say, what if I add another vertex? That vertex can only be connected to one other vertex. Otherwise, it will create a cycle, and therefore it has only one edge. And that's why we always have this. So because the iterative property about how we can build a tree based on their vertices, we actually get this proof. And so that's kind of the idea behind how this actually works out. So we do this really cool theorem for any tree with more than one vertex. It has at least, there's always at least one vertex that has at least vertex of degree one. And namely, we call the leaves, the vertices at the very end that have degree one. And then we have an internal vertex or branch vertex, or sometimes called roots, depending on how they're designed. So let me point to this one. This is a tree. More correctly, this is actually called a caterpillar. I will digress on that one. So we're going to talk about what are the leaves, and I'll then explain what a caterpillar is. So this is a V0 would be a leaf, V8 would be a leaf, V1 would be a leaf. Just what are all the vertices that have degree one? That's really easy to see. Now, there are different ways to have drawn this graph that would actually indicate this idea of what's called a root. So a root is a vertex from which all others flow. So I could have done right here where I had V1 and it comes down to V5 and V6 and V3. And then this one has three vertices. This one has two. And if I drew it like this, that would make V1 the root. But what if I drew V6 so it was up here? So it was above and then V1 came out of it. These are all different options. And because of that, it becomes really, really hard to identify the differences between them, unless there's just one central vertex and everything else is a leaf. But there's another reason I mentioned that this is called actually a caterpillar. And the reason for that is I could draw this. I could have V8 right here, V6. I could draw this as a straight of a line as I can do V1, V3, and V4. And if I draw this path in a perfectly straight line, notice that all of the other vertices come off of this path. Kind of like a caterpillar with its legs coming off to the sides. I know it doesn't have the right number of legs, but it doesn't matter. That's not why we call it caterpillars. We actually call a lot of different trees, some common names, in case you're curious, are caterpillars, cacti, cactuses, lobsters, and many others. They're often named after just things what the graph kind of looks like, and it makes more sense if you actually could see what what all these different options are. Go ahead and Google them. They're fun, and they're actually whole fun classes of graphs to kind of work with. All right, getting back to this, one last thing. Let's just go back to this theorem right here. For any tree n, it has n minus 1 edges. So the really nice part is if I have 10 vertices and 12 edges, is it a tree? The answer is no, because if it has 10 vertices, it would only have 9 edges. That's what this theorem is all about. So if you simply know the number of vertices and the number of edges, then you know whether it is a tree or not. Also, can you find all the isomorphic trees with 4 degrees? So I'm going to have 4 vertices. Sorry, not 4 degrees, 4 vertices. And so if I actually drew 4 vertices, 1, 2, 3, 4. Well, let's think about this. This vertex, if it's connected down here, let's just connect. It has to be connected to this vertex. It has to be connected somehow. So that labeling will suppose that these 2 vertices are now connected. That's really ugly. I'm gonna get rid of all those. Now the question is, how is this vertex connected? It has 2 options. It can connect here, it can connect here. Because if we're going to add them in one vertex at a time, it doesn't really matter how I add what the order is, you're going to end up with the same idea. So we have 2 different scenarios here. So let's just play out both those scenarios. So scenario 1, we had here, and then we had here, and then scenario 2, we'll call it this one. I'll get rid of this other dotted line. All right, so with that said, now I got to add this third one in. I mean, this fourth vertex. It has a couple different options. Option 1, it can connect here, it can connect here, or it can connect up here in this graph. If it connects either of these 2 ones right here, either of these options, it's actually the same thing. In that case, it would just, all the vertices would end up looking, because if they're unlabeled, this whole graph isomorphism idea, they're just going to be a perfect path of vertices. And that gives me the degree sequence, notice, of 1, 2, 2, 1, 1, i.e. this degree sequence. On the other hand, that this number right here, so let's let that would be that option. So let's kind of get rid of those options. Now let's look at our third option. If it comes out of this one, I essentially now have the vertex where I have a central vertex and everything's coming off of it. And that would have the degree sequence 3, 1, 1, 1. Oh, wait a minute. Then when I'm looking at this, if I come here, well, this has 2 options. Well, 3 options again. Either it connects to this one, which would give it this connects up here, or it connects down here, but those either ones would end up right here. So for that reason, our only 2 isomorphic graphs, non-isomorphic graphs, because everything else is just isomorphic between these 2, are those 2 graphs right there. So that's why degree sequence doesn't guarantee isomorphism, by the way, but it's the first thing we check. If the degree sequences do not equate each other, we have a massive problem. All right, I hope that helps you understand trees a little better. Let me know what questions you have, and good luck.